Come on in. Feel free to ask me any questions. We got about a couple minutes left right now.
Hey, Professor.
Hey, what's going on?
Hey, this is John. Now,
Yes.
I sent a text earlier about the test tonight.
Right.
Right.
So
Um,
I
am I
saw that
able
you said you prefer to do it at testing centers. Is that still cool?
yeah, I can do it at a testing center. I live like a stone's throw away from the Chesapeake campus,
That's cool.
so I can really do it anytime tomorrow.
Okay.
So, do I have to
I'll
set
set
up
it up for you.
a appointment?
That's cool. I'll set it up tonight and I'll just make it available for you anytime tomorrow. I
Okay.
will be making a different one, but definitely don't talk to anybody about what's on the test because there may be some overlap. It's really hard to try to make two tests that are equivalently difficult without using quite a few questions that are the same. So I'm sure it'll have some questions.
Yeah, that's not a problem.
All right. Good
I
luck.
appreciate it.
Hope
All right.
everything
Thank you.
works out all right. All right. Looks like 520's arrived. Anybody have any questions? Oh, did you get my text email over the break? Mitchell. I think he might have been the person that I remember seeing. Let me see if I remember. The only way that you could take it at home is if you have an extensive drive. So I've been allowing that for people that have really long drives. And then when you have to do that, you have to have a big mirror behind you so that I can see, like, basically sort of from this angle. I need to see like your hands, a little bit of the screen, but mainly if anything in your lap, I need to be able to see that. So you have to have a Respondus lockdown browser with a Respondus monitor running as well. So you also need a webcam and that kind of stuff. So that's been the only way I've been allowing people to do that is if they have a significant drive and otherwise they don't come on the campus except for labs. So if you want to try to qualify that way, you can. Like I said, I have people coming from, like, I drive from North Carolina, people drive from Eastern Shore, stuff like that. Then I usually try to make sure they can do it. But you would have to have a good sized mirror behind you that I could look through the webcam and see, like I said, uh, to some extent the screen, but that's not really what's important. It's more important what's going on right here in the area where your camera can't catch. Uh, as luck would have it, whenever you give a freedom, someone's got to take advantage of it, and now I can't. Now I can't just let it go with people taking it at home without some kind of mirror set up for that. Uh, yeah, I
Excuse me, Professor.
by the way, and Kathy, you said, go ahead, Darnisha. Sorry.
I've been noticing in the grade book that the Logan at home browser test actually is affecting my overall grades.
Yes, that will, but it won't for very long. It just gonna have to be there for a split second or whatever. So, uh, actually, I might even be able to change it now. Let me go ahead and do that because what I do is transport the grade after they make it. But I can go ahead and fix that so you don't, have a panic attack.
Okay, thank you.
You're welcome. Anybody else have any questions? All right, so remember this exam, one of the capstone problems of this exam, and is in fact part of this exam, is your ability to do what I call the paradigm, whereas you use Gauss's law or Coulomb's law to derive the electric field of a charge distribution. Then you use V, or delta V is equal to V is equal to the negative integral of E dot dl. To compute the voltage difference from the positive charge part of a capacitor to the negative charge part of the capacitor. And then you use C equals Q over V to determine the capacitance of that capacitor. That's like I said, a three-step process you got to be able to do. That's very much on the exam agenda. I very much did those ad nauseum last meeting, but we still have some other stuff left for chapter 7, so I want to make sure I hit those in case you had any problems. As far as you that are asking me questions about lockdown browsers and text and stuff, let's save that towards the end. You can ask me at the end. I need to get jumping into chapter 7. I've put up enough videos where you've seen enough stuff from chapter 7, but to be honest with you, or excuse me, chapter 7 from chapter 24, but to be honest with you, the stuff that's most important is you've got to be able to find equivalent capacitances for capacitors in series, for capacitors in parallel, as well as for a whole number of capacitors, some of which are in series with others, and some of which are parallel to others. You have to know how to use the actual energy equations, which is how much energy stored in a capacitor. And the formula I always start with is 1/2 CV squared, because it looks just like 1/2 MV squared, and it looks just like 1/2 KX squared, which is a big parallel that's going to come in handy later. And then finally, of course, you need to be able to use the capacitance C equals Q over V, as well as the capacitance for a parallel plate capacitor is epsilon 0 A over D, or if you actually have a dielectric, it would be K times epsilon 0 times A over D, or instead of K times epsilon 0, you can just write it as epsilon. So all these equations that I just mentioned will be shown when I first share my screen. So just be prepared for that. I'm getting ready to work a problem where I'm going to reduce a set of capacitors down to an equivalent capacitance. So let me go ahead and share the screen on that. Like I said, save your questions as far as that other stuff goes towards the end. And I hope you all do really well on your exam, but let's get started on this. So I've clicked share screen. Yay, it didn't make me download something again. Okay. So what I have drawn, once you finally get to see my iPad, is you see a battery on the far left hand side. You actually see the equations above the purple line. Those are the equations I said you need to be able to make use of for the exam tonight. Of course, they're included on your on your equation sheet that is sort of packed within your test. So we've got that covered that way. But also, like I said, you do need to be able to use the formulas for a bunch of capacitors in series. So unlike the resistors that we learned about earlier, when you have a bunch of capacitors in series, their reciprocals add to give you the reciprocal of the equivalent. And when you have a bunch of them in parallel, their actual capacitances add. So it's exactly the opposite the way the resistance works, but it's the same sort of rigmarole. That's why I don't feel too terribly bad about you guys doing that, because you've already had some experience doing it with the resistors. So those are the equations up top. I just wanted to reiterate those. What I'm going to start off with is try to find the equivalent capacitance of this bank of capacitors here. So what I want to know is C equivalent of all that stuff is equal to question mark. Now I wrote the first one as 1.0 microfarads, and that's pretty much what I'm doing for all of them. I just didn't want to waste time writing the units every time. So each of these are different in capacitance. That helps me make sure you guys don't confuse one for the other. And also, like I said, it makes it a little quicker. So we have formulas, as you can see in the top left. We have formulas for when they're in series, and we have formulas for when they're in parallel. And what you try to do is just one by one start sorting the pairs or more of capacitors that can be combined either by the series formula or the parallel formula, and then keep working it out until you've got all of them reduced down to a single capacitance. So I'm going to start off, for instance, with the 5 and the 6. So what I'll do is say solution. It's going to start right here. I'm going to look at the 5 and 6 microfarad capacitors since they're in parallel. So I'm going to say C 5 comma 6 is supposed to be the equivalent of the two 5 and microfarad and 6 microfarad capacitors. They're in parallel, so the formula is like the series formula for resistors. So I'm going to say this is in fact 5.0 microfarads plus 6.0 microfarads is equal to 11.0 microfarads. What that means is now I can replace this whole setup with that one guy still, these two guys still, and now instead of that bank of capacitors right there, I'm going to have 11.0 microfarad capacitor there. And that's it. So I've gotten that. Now I have this 2.0 and 3.0, which are in series, and therefore I want to find the equivalent of that. I'll call it C2 comma 3, and we know that the reciprocals add to give the reciprocals, so that'd be 1 over 2.0 plus 1 over 3.0. Which equals, of course, what you do is you check and see, does the 2 go into the bigger denominator, 2 does not go into 3, then you try multiples of 3. So 2 does go into 6, so if I multiply 1 over 2 by 3 over 3, then I get 3.0 over 6.0. And if I multiply 1 over 3 by 2 over 2, I get 2.0 over 6.0, which in fact gives me 3 plus 2 over 6 is 5.0 over 6.0. So finally, I can say that the equivalent of 2, 3 is actually 6 over 5, which is 1.20 microfarads. Okay, so now I can replace this again with this capacitor right here. And then in place of these two capacitors, I'm going to put one capacitor that has a capacitance of 1.20. And then opposite it is this capacitor of 4.0. And then after that, I got the capacitance of 11.0. And that's basically the equivalent circuit now. And I can put all that together like this. Okay, so now I have a 1.20 and a 4.0 that are in parallel, so I'm going to go ahead and attack those. I'll call this C 1.2 comma 4. And of course they're in parallel, which means they add. So this is going to be 1.20 microfarads plus 4.0 microfarads, which is equal to 5.20 microfarads. So now I can replace all this with basically a capacitor right here that we know is 1.0 microfarads. Then we've got the equivalent of the 1.2 and the 4.0, which is 5.20. And then we got the equivalent of the 5 and the 6, which is 11.0. And then all these guys will come back and run into the battery as such. And this is a battery. Doesn't look like one because I drew the arms a little short. Anyways, that's pretty good there. Now what I have is just 3 capacitors in series. So I know that 1 over, let's go back to purple. I know that 1 over C equivalent. And this is the final C equivalent. In other words, when I'm done with this, I'm going to have one C equivalent that represents all of the capacitors that I had to begin with. So I know that 1 over C equivalent is equal to 1 over 1.0 plus 1 over 5.20 plus 1 over 11.0. Now, that's not the easiest thing to deal with, but in principle, I could just, well, actually, yeah, I'll just use a calculator and compute what they are and then flip it over. So 1 over 1 is obviously going to be 1.0. 1 over 5.20 is equal to 0.193. And I'll go one more sig fig with that and call it 1931. And then 1 over 11, I think you all know what that is. And you get 0.0909. That gives me 3 sig figs, so I'll say put a 1 on the end of that. And all of that gives me plus 0.19231 plus 1. So I basically added the 0.9090 and the 0.19231 and the 1, and that gave me 1.283 and then 2. So that's 5 sig figs, way more than enough, in other words. Now I can just say that C equivalent is the reciprocal of that. So I'll say raise it to the -1 power, and that gives me 0.779 microfarads. So this whole circuit is in fact equivalent to a battery with a single capacitance, and that single capacitance is 0.779 microfarads. Now I'm not testing you tonight on your ability to now put all this back together and figure out, how much voltage is on each capacitor and all that good stuff. So I'm not going to take the time to show you that tonight, but there's plenty of videos on my YouTube channel for you to check out on that, and that would be relevant to the next tests that you have, not to this one anyways. So what we've done is we've basically replaced 6 capacitors with a single capacitor and found the equivalent capacitance, and that's the answer right there. Anybody have any questions on that? Hopefully I didn't make any careless arithmetic mistakes. That's always a problem. One thing I will say about further figuring out voltages and stuff like that, now that you have that 0.779 microfarad capacitor, you can use C equals Q over V, the definition of capacitance, to solve for the Q, because the V would be whatever voltage the battery had. So if it's a 12-volt battery, for instance, then you'd say Q equals 12 volts times 0.779 microfarads, and that'll give you a certain number of microcoulombs of charge. That happens to be exactly the same amount of charge that leaves the positive side, or that we pretend leaves the positive side of the battery. And since it's uninhibited and the path doesn't separate from anything before it gets to the 1 microfarad capacitor, that in fact is going to be the very charge that the 1 microfarad capacitor will develop on its left hand side, and then that's going to force the exact opposite, in other words a negative of that same amount of charge, to appear on the right hand side of the 1 microfarad capacitor. And then that same amount of charge, part of it will go to the top leg of the 2 and 3 microfarad capacitors, and then the other part will go into the 4 microfarad capacitor. And conservation of charge is an issue, so that's why I'm saying whatever charge that is, part of it's going to the top and the other part's going to the bottom, so that the charge that the 2 and the 3 have just one of them will add to the charge that the 4 microfarad capacitor has to give you the charge that the 1 microfarad capacitor has. So that's sort of the process about going through that. Like I said, you can check out examples of that. Do a search for just capacitance probably on my YouTube channel. You'll find plenty of those. So no questions on this one? All right, so we've done that. You know how to do it. Hopefully it's pretty straightforward. In fact, I usually, because these are neat problems, they're good problems, and they require you to show your knowledge and your ability to do basic algebra and stuff like that. I usually value them pretty well and have a couple of these on every test just to make sure you guys know what you're doing. So make sure y'all are up to speed on this. Look at a couple of these from chapter 24 in the chapter quizzes if you want before you take it, and that'll give you some help. All right. Now that we've done that, I'm going to solve something else, which is not unlike what your book does. Your book has one where it's called capacitors reconnected. So what we're going to do here is we're going to imagine that there's a battery right here. That battery, let's say, is 24.0 volts. Okay. And then it breaks apart. You can imagine, for instance, the positive side of the battery sending out positive charges, and those positive charges, some fraction of them are going to this first capacitor, and that capacitor has a capacitance of 1.00 nanofarads. And then the other part of the charge that left the battery will in fact go to this capacitor, and this capacitor is going to have a 5.00 nanofarad capacitance. And I'm making those one as a clear multiple of the other so that you can reach certain conclusions, like for instance, when we had resistors in series, you sort of had some sense whether the majority of the current would go in the bigger resistor if they were in I said series, but I meant parallel. So if you had two resistors in parallel, you reach some conclusion from doing labs earlier that a certain amount of current would go into the bigger resistor and a different amount of current would go in the smaller resistor. Hopefully y'all remember that in fact the bigger resistor gets the smaller amount of current and the smaller resistor gets the bigger amount of current. I want you to see something similar to that happens with capacitances when they're in parallel, and I want you to recognize what that is. Is it the actual charge, or is it the voltage, or what? Okay, so what we're going to do first is one, charge the capacitors. Two, I'm going to calculate V1, which is the voltage across capacitor of 1 microfarad or nanofarad. V5, which is the voltage across the 5 nanofarad. Q1, the charge on the 1 nanofarad, and then Q5, the charge on the 5 nanofarad capacitor. Then 3, I'm going to disconnect them. Disconnect from battery. Disconnect from each other. Reverse one capacitor. And reconnect. And then 4, I want to know V1 prime, V5 prime, Q1 prime, Q5 prime. In other words, they're going to have new values of voltages and charges after this process is done. I want to calculate that too. So that's really what I'm trying to work out here. This is not the kind of problem that that you might think is helpful for you to understand, what circuits do and what capacitors are for. This is really one to help you understand how actual capacitors behave. So let's go ahead and look at what's happening here. So in this situation with this circuit, you have a 24-volt battery on the far left-hand side. We use conventional current, which is the mythology that positive charges leave from the positive side of the battery, go around the circuit, and then come back in the negative side. We actually know it's really negative charges leaving in some sense, like it's leaving the negative side of the battery, going the other way, but you really can't do anything to detect that other than do something called the Hall effect. So we can ignore that. But what's going to happen is a certain number of charges or a certain number of positive charges are going to leave the positive side of the battery, and some fraction of them is going to the 1 nanofarad capacitor, and the other fraction is going to the 5 nanofarad capacitor. Now, if you wanted to find out the total amount of charge that's going to the two, then what you do is find the equivalent capacitance of these two, and then stick those two in, or stick that equivalent capacitance in series with a battery. Use C equals Q over V to calculate the charge, and that's the total charge that would leave the battery. Then you'd have to use the fact that these two batteries or these two capacitors are in parallel so that they have the same voltage, and you could use that to figure out what amount of charge the 1 nanofarad capacitor gets versus what amount of charge the 5 nanofarad capacitor gets. So that's the way we could actually do it. Let's do right here, solution. So what we're looking at right now is number 2. I'll say C equivalent is equal to 1.00 nanofarad plus 5.00 nanofarad, which is equal to 6.00 nanofarad. Then we can say C equals Q over V implies Q equivalent would equal C equivalent times V, which in fact would be 6.00 nanofarads times 24.0 volts. Notice how I don't do anything with the nano prefix, because that means times 10 to the negative 9th, for instance. So I can just leave it there because a coulomb's a big unit of charge. So a nanocoulomb or a nanofarad multiplied by a volt gives me a nanocoulomb. Okay. So I'm going to do 6 times 24, which you guys know is 144. So this is going to be 144. That's 3 sig figs. So I add one more dot 0. Okay. So that's one extra digit that's not a sig fig. And what we got is 144 nanocoulombs is the net charge. Now, when that happens, what that means is a certain amount of charge will go on this one, and let's say a certain amount of charge will go on this one as well. Those two amounts of charge, the one that goes in the 5 and the one that goes to the 1, add up to give you 144 nanocoulombs. Okay. Well, how do we figure out what that is? Well, what we know is that Q1 plus Q5 has got to equal 144.0 nanocoulombs, but we also know V1 is equal to V5, which according to the C equals Q over V means Q1 over C1 is equal to Q5 over C5. So that's two equations, two unknowns. We can clearly work this out, not a problem. In fact, what I'm going to do is I'm going to solve for Q5. And what we'll see is Q5 is in fact equal to C5 over C1 times Q1. Of course, C5 is just 5 nanofarads, and C1 is 1 nanofarad. So the C5 over C1 is just equal to 5 Q1. So now I can plug this in. So Q1 plus 5 Q1 is equal to 144.0 nanocoulombs. That gives me Q1 is equal to 144.0 nanocoulombs divided by 6.00. We know, of course, that the 5.00 divided by the 1.00 gives us 3 sig figs. So I can actually put a 4th sig fig down there and just underline it. So now I'm going to take the 144 and divide it by 6, and we get, of course, 24, which is 24.0. And in this case, it turns out to be 24.00. And this, of course, is nano coulombs. Okay, so now we've got Q1, and we know Q5 is 5 times as much. So Q5 is equal to 5 times Q1. That gives me, of course, 5 times 20 would be 100, and 5 times 4 would be 20. So this would be 120.0. Whoa, that's really some bad looking right in there. Hold on there. 120.0 nanocoulombs. So our answers are Q1 is equal to 24.0 nanocoulombs to the proper number of sig figs. Q5 is equal to 120.0 nanocoulombs, and V1 is equal to V5 is equal to, now in this case, all I have to do is take Q1 and divide it by C1, or Q5 and divide it by C5. So I'll say Q1 looks nice. I'm going to say that's 24.00 nanocoulombs. And I'm going to divide that by C5, or excuse me, that was C1. Sorry about that. Or that was Q1. So I'm going to divide that by C1. And C1, of course, we found was, oh, that was 1 coulomb. Oops. 1 nanofarad. In this case, the nanos cancel out, and you get 24 divided by 1, which is just 24.0 volts. So now we've gotten all 3 answers, or actually all 4 answers. And this was from part 2. Any questions on that part? Okay. Y'all see how that went? You just have a couple equations you can use, and that tells you, not only that, you should look back and realize, oh, wow, the one with the 5 nanofarads, in fact, had 5 times as much charge as the one with 1 nanofarad. So yeah, the bigger capacitor actually gets the bigger charge. And that's because the bigger capacitor carries the largest amount of energy. On the other hand, we did resistances. It took the most energy to go through the largest resistance, so the smallest current would go through it. So it's sort of opposite to resistors, just like we expected. All right, now what we're going to do is we're going to take what we just learned, and we're going to build this circuit again. So now what I have is I've got a capacitor right here, and that capacitor has a capacitance of 1.00 nanofarads, and it's been disconnected, if you will, from the battery as well as from the other capacitor. And then there's another capacitor over here. And its capacitance, of course, is 5.00 nanofarads. But now we're actually going to flip them. So we're actually connecting them backwards. So before I had, for instance, the positive charges on the top plate for both cases. In this case, now I'm going to put the positive charges on the bottom plate for the 5 nanofarad capacitance. And what that's going to cause is Q1, well, let's say Q5 minus, and actually I'm supposed to be writing in purple. Let's say Q5, which is the bigger one, minus Q1 is going to be equal to the new charge Q. And that new charge, of course, is also going to be the charge of the two when they're combined. So for instance, now I'm going to have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4 like this. And ultimately we're going to have the actual capacitors in connection with each other, and it'll force the tops to become a positive charge and the bottom to become a negative charge. So notice the Q5 minus Q1, that's because basically when I connect them like I have drawn here with the purple and the purple pluses and minuses, you see that a certain number of the pluses will cancel out a certain number of the minuses. And that's why I did big number minus small number, i.e. Q5 minus Q1. So when I take 120 minus 24, that gives me 96. So this is going to be 96.0. And technically that 0 is not a sig fig, and that's going to be nanocoulombs. But what's going to happen is once they equilibrate, we're going to get the top to have a charge of positive Q 1 prime, and the top on the other side is going to have a positive Q5 prime. Okay, so what that tells us is this is also equal to Q1 prime plus Q5 prime. That's the key to this whole thing, is figuring out, oh, when I combine these two and reconnect them in the opposite way they were, which is what I did with this little flap right here, okay? When I do that, then the excess charges, which in one case will be positive, in the other case will be negative, those excess charges will appear as the amount of charge that one side has, let it be positive, and then the other side will have the same amount, but it'll be negative. So that's what we're looking at now. That's why I put the plus Q1 and plus Q5 over there. So what we know is Q1, actually I should be using Q1 prime plus Q5 prime is equal to 96.0 nanocoulombs. But we also noticed that if you thought about what the voltage is on the top plate of the 1 nanofarad capacitor, the only thing that differs from the top plate of the 1 nanofarad capacitor to the top plate of the 5 nanofarad capacitor is that there's only wire connected between them, and the resistance of wires is negligible compared to just about everything. It's not zero, of course, but it's still about the same. And when you get that in your head, then you realize, oh, wait a second, the top plates have the exact same voltage as each other, and the two negative plates have the exact same voltages of each other. So in fact, this is basically a parallel configuration because they have the same voltage. With that in mind, we can say V1 prime equals V5 prime, which equals Q5 prime over C5, and that's of course equal to Q1 prime over C1. So again, like I did last time, I'm going to say Q5 prime is in fact going to be C5 over C1 times Q1 prime. Now I can plug this into this. And from that, I'm going to get Q1, and remember C5 is 5 and C1 is 1, so 5 divided by 1 gives you 5, so I'm going to have Q1 prime plus 5 Q1 prime is equal to 96.0 nanocoulombs. Again, only 0 decimal places on that are significant. So from this, we can see that Q1 prime is going to equal 96.0 nanocoulombs divided by 6.00. So 96 divided by 6 is 16. So this is going to give me 16.0 nanocoulombs. And of course, that's 2 sig figs divided by 3. So I only get the ones place, not the tenths place. And then Q5 prime is 5 times Q1 prime. So 5 times 16 is 50 plus 30, which would be 80. So this is 80.0 nanocoulombs there. And you see that 80 plus 16 does give me 96. So I've got those two. And now I can see that V1 prime, which is equal to V5 prime, which is equal to, again, I'll take the Q1. So the Q1 was 16.0 nanocoulombs divided by the 1.00 nanofarads, and that gives me in fact 16.0 volts. Again, not the right number of sig figs, but now we got it. So finally, I can say that Q1 prime is equal to 16.0 nanocoulombs. Q5 prime is equal to 80.0 nanocoulombs, and V1 prime equals V5 prime is equal to 16.0 volts. Now, this is decidedly not on the exam today. This is just another problem we needed to do from the chapter 24. So I like I said, I'm just trying to press on. We'll finish up chapter 24 next class meeting and probably jump into 25, but I want to make sure you know how to do this. Okay, any questions on this one? So this one gave us a lot of different things to look at. It does help you to some extent understand how a capacitor behaves when you connect a battery to it. I'll cover that a little bit more next time. But the other problem I want to work is another problem that's not, again, this one right here is not on the exam that you're taking tonight. The kind of stuff that I did right here is, okay? This is not, this is. The next problem I'm going to work also is not to be covered tonight on the exam, but it is, again, something very important from the chapter and some of the best problems I know of in the whole book. So what I'm going to do is imagine a parallel plate capacitor, and I'm going to connect it to a voltage source. So let's do this. I'm going to draw a parallel plate capacitor. Let's say I'll draw it right here. And then I'm going to draw the other plate right here. Now I'm not really drawing them to an appropriate scale because really the distance between them should be very, very small compared to their length and width. And I've sort of drawn it a little bit bigger in terms of their distance between them. That should actually be a little bit smaller, but anyways, I think y'all get it. So this is going to go here. This is going to go here. Okay. What we have connected here is the power source. And the power source is connected to the or is a battery. And that battery has a voltage V. I'm going to say this plate has an area A, this plate has an area A, and in fact, let's call the separation between these two guys, let's call this separation just plain X. Okay? So what I'm going to do is take this setup, and then I'm going to force these two plates to be pulled apart. Okay? So what I'm going to do now is I'm going to put one plate right here, from here to here. And right now it's like 2 squares apart. I'm going to make it look like, 6 or 7 squares apart, something like that. Okay. Now, obviously, when I do this, the plates of the capacitor will have to actually be quite a bit larger in height and depth. In other words, from here to there. Okay. Did that work right? Or that did not work right. Okay, like that. So this is now our parallel plate capacitors. Something like this. Actually, I went across 2 the last time. I went across 2 this time. So, okay, that's okay. So this is still going to have an area A. This is still going to have an area A. And here's my power source. I'm going to maintain the connection with the battery, and that's important. That's going to be something that we have to think about a lot as the course progresses. Okay. But now what's happening is this distance I'm going to say is 4x. In other words, I just pulled these two plates apart and took them from a distance x apart to a distance of 4x apart. And I need to calculate some things. Specifically, I'd like to know, one, what's the energy in the capacitor before and after? So A, what is U initial and U final? Okay, so this is the final case, and this is the initial case. So I'm going to calculate those. Then what I want to do is calculate how much work is required to pull them apart. That's a question mark. And then finally, I want to find out how much energy is exchanged with the battery. So C, how much E, energy, might as well write it out because somebody's going to mistake it for an E field, is exchanged with the battery. Okay, so that's what we're trying to do. Anybody have any questions about that? Okay. All right. Well, let's start with the U initial. So U initial is 1/2 CV squared. Remember, that's what I always uh, start off with, because that's the formula that looks most like the ones we're familiar with, specifically 1/2 mx or mv squared plus 1/2 or excuse me, 1/2 kx squared. So it looks just like that. So if I plug this in, I'm going to say 1/2. Oops. I'm going to say 1/2, and then the capacitance of a parallel plate capacitor is just supposed to be epsilon 0 A over the separation, which in the first case is X, and then the voltage is just plain V, so it'll be V squared. So I get 1/2 epsilon 0 A V squared over X is the initial potential energy. In other words, that's the energy stored in the capacitors. And that's pretty much what we often use the capacitors for. Is they're like a battery, but a battery that can expel all of its energy in a fast incident, whereas batteries normally trickle out slowly, which is a good thing if you're actually using the battery to like run your phone. But if you need all the power at once, say to start a car or something, then yeah, it'd be helpful to have a capacitor as opposed. Okay. All right, so now let's look at the final energy. In other words, the energy in the capacitor in the final configuration, that's also 1/2 CV squared. And that means it's going to be 1/2 epsilon 0 A. This time it's over 4x though. And since we kept the battery connected, the voltage stayed the same, but that also allows charges to flow in and out back and forth. So with that in mind, I can say it's 1/2 epsilon 0 A V squared over 4x, which ends up becoming basically 1/4 of U initial, and that's U final. So I've written it a couple different ways, and that'll come in handy as well. Any questions on that? All right, so now I can figure out what the change in energy of the capacitors is. So the change in energy, I again keep writing in red by mistake. So delta U capacitor is the change in potential energy of the capacitor, which is U final minus U initial. And of course, U final is 1/4 U initial minus U initial. So 1/4 minus 4/4 is 3/4 U initial, which is going to be 3/4 times 1/2 times epsilon 0 A V squared over X. And I think we can see that that's going to be 3/8 epsilon 0 A V squared over X. And this will come in handy later, because basically what we're going to do is we're going to say the total potential energy, which is delta U cap, changes by an amount delta U. The total energy of the battery changes by an amount delta U battery or delta E battery or something like that. And then that is all equal to the work put in. So we can use that to solve for the battery. So that's where that's going to come in handy. So we've now done part A. And we actually did something for part C that wasn't really asked for, but we've already done it, so it's kind of nice. Now I've got to do part B. And for part B, what we want to know is work is equal to the integral of F dot dl, which in this case, I'm pulling it probably left and right. The actual plate of the capacitor is going to move left and right. So there's really no need to concern ourselves with the dot product part. And the fact that the electric field created by a parallel plate capacitor is constant tells us that a lot of the problems with the actual integration are not even going to be existent. So I'm going to change this from F to Q times E. And I'm going to say it's the integral of Q times the electric field times dl. Okay. Now, what we have to remember is that when we computed the electric field inside of a parallel plate capacitor, we got this plate, let's say the positive plate, calls the electric field to point to the right, and its value was sigma over 2 epsilon naught, pointing to the right. The negative plate, however, that also created an electric field E negative that also pointed to the right, and it was sigma over 2 epsilon naught to the right. Okay, so what that reminds us is that one of these plates creates half the electric field, the other plate creates the other half. What we're trying to do is we're going to think sort of like the left half is creating the field, and of course it can't create the whole field, it can only create half of it, whereas the right plate is a charge that's going to be moved in it. So that's what I'm shooting for here. So let me write that down. Left plate creates the E field, half of total, and the right plate acts like a charge Q. Okay, so with that in mind, what I'm going to say now is I get the integral of, now here's what I'm going to make use of. C equals Q over V tells us that Q is equal to CV, and of course the C is epsilon, whoa, I wrote epsilon backwards. It's epsilon 0 A over D, or excuse me, epsilon 0 A over X for any particular separation X, and then times the voltage V. Okay, so that means I've got an epsilon 0 A over X times V for the charge. And then I also have the electric field for the whole thing, which, remember, the electric field is basically when you integrated the electric field, which was a constant, over a distance, let's say L, then what we got was V is equal to E times L. So E is actually just V over the separation distance, but we need half of that. So what I'm going to say is this is V over 2, that makes for the half, and then divided by the separation, which at all times is going to be X, like so. So there's my electric field, and then my dl is just going to be dx. And I'm going to integrate from X to 4X. Any questions on that part? Okay, so we get epsilon A V squared over 2 is all the stuff that comes out in front, and then I've got an integral of dx over x squared, and that's from X to 4X. Now the integral of x to the negative 2 power is negative 1 over x to the negative 1 power. So I'm going to say this becomes negative epsilon 0 A V squared over 2. I put the negative out in front, that accounts for it. And now I've got to do 1 over x, which would be 1 over 4x minus 1 over x. Okay, so to make a common denominator, we multiply by 4 over 4 in the second term, the minus 1 over x term, and 1 over 4x minus 4 over 4x is negative 3 over 4x. That gets rid of that negative, so I can finally say that the work W is equal to a positive. Now we're going to get a 3/4, so I'm going to make it, in fact, 3/8 because there's a 2 down there already. That's going to be a 3/8 epsilon 0 a v squared over x. That's the entire work done. And in fact, we can compare that a little bit, for instance, to the initial energy, which was epsilon 0 a v squared over 2x. So we could say it's actually equal to 3/4 of ui if we wanted, because then that would actually give us the same amount. Okay, so we've now calculated the work done in separating them. Notice it's a positive amount of work. Hopefully you all expected that, because remember, a parallel plate capacitor has a positive plate and a negative plate of equal magnitudes but opposite signs. That means they're attractive, and in fact I'd have to put some force into separating them because they want to get closer together. So now I can do part C, and part C is basically the part where we're calculating the energy put into the battery. So what we're going to say is that the work put in is equal to the change in the energy of the capacitor plus the change in the energy of the battery. So I'm going to say plus, that is just the most terrible looking plus symbol I've ever written. First off, let me fix the X that I jacked up. Okay. So it's delta U of the capacitor plus delta U of the battery. That means delta U of the battery is equal to the work minus delta U of the capacitor. Well, the work, we can call that 3/4 U sub I, and the delta U of the capacitor we found was in fact the same quantity. I think, let's see, delta U capacitor, that gave me 3/8 over, did I do all that right? That is right. Okay, so let's not use it as that. I'll go ahead and I'll put it in as the actual energy amount instead of the, in terms of the UI, just in case I made any careless mistakes. So this is going to be 3/8 epsilon 0 a v squared over x, and then minus the delta U cap, which we found was positive. I did find it was positive, right? 1/4 minus, oh no, that was supposed to be negative. That's the problem. That's where everything was going wrong. Notice down here, everybody, when I did the delta U cap, it was U final minus U initial, which is 1/4 UI minus UI, which would have been negative 3/4, which would have been negative, which would have been negative. So that's going to make this one negative 3/8 epsilon 0 a v squared over x, which you can now see it's 3/8 plus 3/8, which would be 6/8. And of course, 6/8 is the same thing as 3/4. Yeah. So the ultimate answer is 3/4 epsilon 0 a v squared over x. And that's the energy, darn it. That's the energy delivered to the battery, which we call delta U battery. Anybody have any questions on that one? Okay, like I said, your book has an example like this. This is not on tonight's exam, so don't worry about that. But you should be able to find something very much like it in the book. I think I changed. I don't even think I changed the letters necessarily. I know I changed the distance of separation that I made them. I think the book went from X to 3x or X to 2x or something, and then I did from X to 4x. So it's pretty much the same. Anyways, but we do see that we are in some sense actually charging up the battery, and that's a way in principle that you could charge a battery is just by connecting it to a capacitor and then pulling the plates of the capacitor apart, and that actually charges the battery. I wouldn't do it very much because sometimes batteries aren't meant to be charged and they get hot and they explode, and that's a problem. All right, anybody have any questions on that? Okay, so I've talked to you a little bit about what happens when you actually add a dielectric to a capacitor, specifically a parallel plate capacitor. But in reality, it's actually any capacitor. If you just add a dielectric, you're going to, in principle, increase the capacitance by some factor. And your book has a table with dielectric constants in it and all sorts of good stuff like that. But I want to talk about molecularly on the micro scale what's actually going on. So let's start off with reiterating what the formulas are. So the capacitance for a parallel plate capacitor is epsilon 0 A over D, and that is in fact for a parallel plate capacitor like this. And actually I drew that a little badly. Let's fix this a little bit. Okay, if you imagine these plates are really, really close to each other, then you do get the adjustment that we talked about where the electric field is essentially a constant except near the edges. Okay, but this one actually has an area A and a distance of separation D, and it just has air or a vacuum between it. Okay, because it turns out epsilon 0 is really very close to epsilon for the air. It's like, I think if I remember correctly, it's like a difference of a 1 in the third decimal place. So you'd have epsilon 0 would be some number, and then if you add 0.001 to the end of that, then you'd have the epsilon for air. So that's what that is. Now, if you go and put a dielectric in there, that can actually help things, because what happens is when you have a dielectric in between, one, you have a little bit more ability to make the separation between the plates really, really small, because you have a conductor. That's what that's the less fancy word for a dielectric, is basically an insulator or a non-conductor. You have this non-conductor that's even harder to ionize than the air is. That prevents the capacitor from failing when the electric field gets above a certain height that the air would break down in. For most dielectrics, you generally have a higher electric field strength that causes the dielectric to break down, and therefore it gives you that protection. But also, if you're going to take and make the conductive plates of the parallel plate capacitor into things that you could roll up, this actually provides a structural object that you can actually roll up between them and keep them from contacting each other. So that's another nice aspect of having the parallel plate capacitor as well. So, or having the dielectric between them. So in this case, I'm going to imagine having a dielectric between the plates. And this will be the dielectric right here, this little purple slab that we got going on. Okay, but again, we still have an area A and a separation distance D. Now, C is equal to K epsilon 0 A over D, but we sometimes use a generalized epsilon instead of epsilon for a vacuum, which is epsilon 0. We just call it plain epsilon, and we say it's A over D times epsilon, where epsilon is defined to be K times epsilon 0, and this is the dielectric constant. So you are supposed to know this particular part of the stuff for tonight. If someone, for instance, if they give you a parallel plate capacitor and they give you A and D and tell you what the dielectric is, you could look up in principle the dielectric constant, or they give it to you and you then would have to use this formula. So this is completely fair game for the exam tonight. I can't remember whether or not I actually put any on there, but I will tell you that it's fair game. Okay, so that's what the happens when you put a dielectric in there. Now, on a microscopic level, what really happens is, let's look at this and just say this right here is a really large plate of a parallel plate capacitor. And then again, we're looking at a very small area of it. So we might imagine it goes infinitely far away upward and infinitely far away downward, which in reality, as I told you, from a physics standpoint, you just want to be about 10 times closer together than you are from the edge. So maybe the center of it might be 1 centimeter, and as long as all the edges are at least 10 centimeters away, but preferably 100 centimeters away, then you'd be golden. Now, what I'm going to do is I'm going to actually imagine that there's a slight gap, even though there shouldn't be, between the plate and the edge of the dielectric, and show the dielectric this way, even though the dielectric will go on forever too. I'm just trying to tie it off a little bit to show you a particular part of it. So it might not even have been very good for me to draw these edges, but the main thing is actually, yeah, let me erase that just to make it a little more obvious. So we're not actually saying the ends of these, or the dielectric is ending there. We're not saying that. Of course, we didn't really say the plates ended there either. That was sort of the whole point. But anyways, we got it. I guess it's good enough. So what's going to happen is when we charge this up, then this plate that I have on this side is going to accumulate a certain amount of positive charge on it. And this plate over here is going to accumulate a certain amount of negative charge on it, like this. So what we're ultimately going to have is, let's say, positive, 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 and then minus, 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 and minus. And what's this going to do is take this dielectric, which has these atoms in it, which we'll say are maybe 3 wide, something like that. And what's going to happen is a negative side. In other words, we're going to polarize the atoms so that the negative side will be flipped towards the positive plate. And then that's going to cause the adjacent molecule to do the same thing. And then that's going to cause the adjacent molecule to do the same thing, like I show here. So you see how those little atoms or molecules are acting kind of funny due to the strength of the electric field that's been created by the two plates. So we're going to get a negative, positive, negative, positive, negative, positive, like that. That essentially creates something like a negative electric field, or like an electric field pointing in the opposite direction. For instance, the existing electric field is this guy. Remember, we always treat electric fields as if they're created on positive charges and end on negative charges. So you could assume each of these signs where I drew a positive and negative, are going to be an electric field that's due to the electric field in before the dielectric was put in there. And then the other one is just the electric field induced in the dielectric. So what's happened now is, as a result of the dielectric, it's as if a little electric field in the dielectric has been created, pointing the opposite way, like this. Okay, so we can look at the electric field existing beforehand as E0. So in this case, you might actually picture it as this one's just going from there and there, and these guys have an electric field strength E0. And what we do in general is we say that the electric field in the dielectric is equal to the electric field that we had before they put the dielectric in there, minus the induced electric field. So these little red guys are considered E induced. Okay. Now, there is a paragraph in your book that's extremely important, and I highlighted it, but basically what he's saying in the book, I can't find the page right now. What he's saying in the book is that an experiment was done where they charge up a capacitor and then they force the dielectric to be either put in between the plates where it wasn't, or if it's in between the plates already, you pull the dielectric out without stealing any of the charge or messing up the circuit. So it's a very difficult experiment to run. But since we know C is equal to Q over V, and then when we have a dielectric, we get C is equal to the dielectric constant times the original C, C0. Since we know that happens, we need to know basically what happens in general within the circuit. So if we actually create this parallel plate capacitor with a dielectric between it, and then we do an experiment to actually pull out the dielectric and do so very carefully, what we discover is the dielectric will, once removed, will actually decrease the capacitance by a factor of K. Or if you tried to force it in, it would increase the capacitance by a factor of K. So if you do this with a battery connected, so battery connected, force dielectric in, then V cannot change. So what happens is, we know C goes up by a factor of K, so that means Q goes to K times Q. And we might even put a little 0 there to represent the part when it wasn't. Before the dielectric was in there, it's Q0. Now, if we do the same thing without the battery connected, in other words, not only is it not connected to the battery, it's just not connected to anything, then the charge has nowhere to go. So we're going to say force the dielectric in, then V can change, but Q cannot. So V goes from V to V0 over K, because that's the only way that can actually happen. you only have two variables to work with the capacitance. You have the Q and the V. And when the V can't change, that means all the changes got to come from the Q. And when the Q can't change, all the changes got to come from the V. And that's what's happening here. So with that in mind, it turns out that that's not only true when you fill the whole space with the dielectric, it's also true when you fill part of the space with the dielectric. So in fact, we can say that this ultimate electric field in the dielectric is going to become the electric field strength that we had divided by the dielectric constant. And that's specifically because of this particular fact. Remember, the V turns out to be just electric field times D. So with that in mind, we know that's going to be the actual electric field within the dielectric. Now we can solve for E induced. And when we do that, we get E induced is actually equal to E0 times 1 minus 1 over K. And of course, we can also use that in other contexts and think about what happens if we did it with the charge. Then we get a charged, a surface charge density equal to sigma 0 times 1 minus 1 over K. Or we can talk about the whole charge, Q, and say that we'll get an induced charge equal to Q0 times 1 minus 1 over K. So all of these are the big important results that we got from making sense of this experiment and using this right here. So next time, what I will do is I'll work a problem where you actually put in a dielectric, or maybe you pull out a dielectric, or we take a dielectric and have it cover half the volume of the space between the two, or whatever. The main thing is this is what we get. And we can use those. And like I said, I will use them next time, but we're done now. So you guys are free to go. Good luck on your exams tonight. Remember, you do have to do a problem like this guy. No, yeah, a problem like this guy. Or just a simple epsilon 0 A over D or K epsilon 0 A over D problems. Okay, see you, Shonda. Anybody else have any questions? Thanks for coming.
Hi. Oh, can you hear me?
Yes.
Sorry, I had a question. I emailed you earlier. I
Mhm.
saw the Respondus like at home exam. Is it okay to take that instead of coming in person to take it?
So that's what I just finished announcing. If you live
Okay.
in excess of like probably 40 miles away, then yeah, I'll let you do that. But there's a whole process you're supposed to go through. Like you'll have to have a big mirror and stuff of that
Okay.
sort. So do you live a good distance away from your campus?
Yes, and I do have a big mirror. I can
So
I
make
can use
sure
that.
if you're looking, let me kill the share screen right now. Make sure you're looking at me
Mhm.
instead. So I need the mirror to be back here. Like I'm assuming your camera's like up there at the top of the monitor. If it's not, that's okay. Just put it wherever. But the main thing is I need to be able to see sort of this area right around in here. So if you put a big mirror sort of at an angle like this, where I can look through the camera and see your desktop, what your hands are doing, it's not so important that I see the screen because I've got the lockdown browser and all that. But as long as you got a mirror that I can use that way when I look at it, then you'll be fine. So I can let you do that if you'd like. You just have to take it with that particular exam that says, I think it says Logan on it.
Yeah, with the webcam and Respondus. Okay, thank you so much. I was just confirming, just making sure.
You don't have to give me your address, but if you just email me and let me know where you live, maybe just your street name and the city you live in or something like that. That way I can justify that I did it because they drove, you had to drive a long way away.
Okay. All right, thank you.
Okay. Thanks, Abigail. Good luck. Anybody else? Mitchell, did you want to do that as well? I sound like you had kids. I don't think you want to do a test while you're watching the kids.
Me?
Oh no, that's what it is.
I'm trying to wait until everyone leaves because mine is kind of private.
Gotcha. No problem. Reynolds, did you have a question, or Kim Thien?
I have I'm in your other class and I was just trying to hear for the office hours. But
Okay, gotcha. Gotcha. Did you have a question you want to ask me while I'm here then?
like so this is the office hour? Like right after the class is the office
Yeah,
hour, or
it's usually right after the office hour. And if like I have something here to discuss with Miss Mitchell, I can just go to a breakout room and discuss that with her. It's not a problem.
okay. So I just have a question about like because I got stuck on some of the problem on the
Okay.
practice test.
All right. Well, let me do. I'm going to create a breakout room real quick and answer her question in that breakout room, and I'll come back to you. Okay.
Got you.
It shouldn't take but a second, I don't think. Let's see here. I need to create a breakout room. If I can just remember how to do that, I haven't done that in a long time. Breakout rooms. Okay. So, Miss Mitchell, would you like to meet me in the breakout room? I'll meet you there, and I'm going to go ahead and stop the recording because I doubt we need this.